This is Dr. Balaji Rachuri, working as an assistant professor in the Department of Chemistry, Malarade Engineering College, Autonomous. Now I am discussing about the isomerism in organic chemistry. Isomerism is a very important concept to understanding the organic molecular structure in a three-dimensional space. Now I am coming to the definition of isomerism. Isomerism is the two or more organic compounds having same molecular formula but exhibit difference in their chemical and physical property due to the difference in their arrangement of atoms or groups along the carbon skeleton or in the space are called as isomers. The phenomena is known as the isomerism. Based on the different possible structures, the isomerism can be divided into two categories: structural isomerism and stereoisomerism. And further, structural isomerism can be divided into three categories: chain isomerism, position isomerism, and functional isomerism. And also, stereoisomerism can be divided into two categories: geometrical isomerism and optical isomerism. Now I am coming to the chain isomerism. The isomers having the same molecular formula but different carbon chain structures are called as chain isomerism. I will take an example of C5H12. Three different possible carbon chain structure. First one is N-pentane, and second one is isopentane, third one is neopentane. All are having same molecular formula but difference in their chain structure as well as shifting of or substitution of methyl groups. So all three are chain isomers of C5H12. Now coming to the position isomerism, isomers having the same molecular formula but difference in their position of atoms or groups on carbon chain is called as position isomerism. I will take an example: C5, C4, H9, Cl. First possibility, 1-chlorobutane, and second possibility, 2-chlorobutane. If clearly observed, in 1-chlorobutane, chlorine atom attached to the first carbon atom, and in a second molecule, chlorine atom attached to the second carbon atom. Both are having same molecular formula, but different in different positional isomeric structure. Clearly observed in the chlorine atom attached carbon atoms. And also second example, C3H8O. C3H8O also possible with the two positional isomers. Here first one is 1-propanol, second one is 2-propanol. Here OH present at the first carbon atom and second molecule OH present at the second carbon. Both are the positional isomers of C3H8 of O. Next, coming to the functional isomerism. The isomer having the same molecular formula but difference in their functional groups are called as functional isomers. I'll take an example: C3H6O. Here CH3, CH2, CHO called as 1-propanol containing aldehyde functional group. And second possibility, CH3COCH3 is called as 2-propanone. Here containing ketone functional group. Both are having same molecular formula but different functional groups. So 1-propanol and 2-propanol are the two functional isomers of C3H6O and second molecule C2H6O. C2H6O can be written in two functional isomers. First one is ethanol, second one is dimethyl ether. Here ethanol containing alcoholic functional groups and diethyl ether contains ether functional group. Both are having same molecular formula but having different functional group. As per the one of the stereoisomeric concept is geometrical isomerism. In a geometrical isomerism, due to the difference in their arrangement of groups or atom about the double bonded carbon atoms is known as geometrical isomerism. Based on the availability of geometrical isomers can be divided into two categories: cis trans isomers and E and Z isomers. I'm coming to the cis trans isomers. The isomer having the same groups present on the same side of the double bonded carbon atoms is known as cis form, whereas same groups present on the opposite side of the double bonded carbon atoms is known as trans form. It's clearly observed in a cis form, two AA and BB groups are present at the same side of the double bonded carbon atom. And the second possibility, both AA and BBs are present opposite sides of the double bonded system. So it is called as transform. It is very good to understand. For the example, I will take an example of 2-butene. Here 2-butene having two possibilities. First possibility, two methyl groups are present at the same side of the double bonded system is called as 2-butene, cis-2-butene. And second possibility, two methyl groups are present at the opposite side of the double bonded system is called as trans-2-butene. Both cis-2-butene and trans-butenes are the cis-trans isomers of 2-butene. Now coming to the EZ isomerism. In EZ isomerism, the configuration is specified by the relative position of two higher priority groups, present priority groups or atoms on the two carbons of the double bonded system. If double bonded system contains more than two different groups or atoms present in the double bonded system, atoms or groups first considered as a priority number, first given as a priority number as per the sequence rule or Kohn-Ingold-Prolong rule. What is the sequence rule? The higher atomic number or mass having highest priority first. You can take an example: iodine, bromine, chlorine, fluorine. So iodine having highest atomic mass or number, this goes to the higher priority, and then bromine, and then chlorine, and then fluorine. And also different groups like chlorine, SO3H, OH, NHCA3, COOH. Here chlorine having highest atomic number is the first atom attached to directly carbon atom. This goes to the highest priority. And then sulfur is the highest priority when highest atomic number when compared to the oxygen. So SO3H is the highest priority than OH. And also oxygen is the highest atomic mass when compared to the nitrogen atom. So OH is the highest priority when compared to the NHCH3, and NHCH3 is the highest priority when compared to the COOH. This is the sequence rule for the identification of priority of the different groups present in the double bonded carbon system. And then if the two atoms or groups with the highest priorities are present on the same side of the double bonded carbon system, such isomers is known as Z isomer, whereas two atoms or groups with the higher priorities are present on opposite sides of the double bonded carbon system, carbon atoms. Such isomers is known as Z isomer. Okay, it is clearly understanding here. Z isomers, high priority groups are present in the same side of the double bonded system. That is called as Z isomers. And the second possibility, both high priority groups and low priority groups are present on the opposite side of the double bonded system. It is considered as a Z isomer. Now take an example. Double bonded carbon system contains halogen atom, fluorine, chlorine, bromine, iodine. Here, this carbon atom contains bromine, iodine. Here, iodine is a higher priority than bromine, and second carbon contains chlorine and fluorine. Chlorine is a higher priority than fluorine. So both high priority groups are present at the opposite side of the double bonded system. It is considered as a E isomers. And coming to the next possibility, here iodine higher priority, and second carbon chlorine high priority. Both high priority groups are present at the same side of the double bonded system. It is called as Z isomers. Next, coming to the optical isomerism, for a molecule to be optically active, it must have it must have at least one chiral carbon. What is the chiral carbon? The carbon atom bonded to the two different non-equivalent atoms or groups are present in a carbon skeleton. Okay, at least one in carbon skeleton, and also that optically active chiral carbon, it rotates the plane of polarized light either left side or right side, depends upon their group availability or groups. Different groups are present in the carbon chiral center. This is called as optical isomerism, and the phenomena is known as the optical isomerism. Clearly observed here, carbon contains chiral center, means having four different groups like W, X, Y, Z, or all are four different groups. It is considered as a chiral or asymmetric carbon. Like this, I will take an example of lactic acid. A lactic acid central carbon atom contains carboxylic acid group, hydroxyl group, methyl group, and hydrogen group. All are different groups. It has act as a optically active chiral carbon. So different optical active chiral carbon shows different possible structural arrangements. So availability of all possible structural arrangements can be divided into different type of pairs, depends upon their relationship. Majorly two categories. One is the enantiomer. The optical isomers that have non-superimposable mirror images relationship to the each other are called as enantiomer. It is clearly understanding. Can you understanding? Here, black is the carbon atom, and four different colors are four different groups present. It clearly observed in the mirror. It clearly observed in the mirror. All groups are carbon atom at the center is the same, but different. All groups are superimposable, superimposable, and also mirror imaging relationship. Clearly understanding here in D-lactic acid and L-lactic acid. Here D-lactic acid contains four different groups and carbon chiral carbon atom in the central chiral carbon atom. This chiral carbon atom is having R configuration, and that another possibility containing S configuration. Here S configuration, R configuration, both are each other mirror imaging relationship, and one molecule is connected reflected to the another one molecule is attached to the another molecule, not superimposable. So both are the non superimposable but mirror image relationship. It is called as a enantiomeric enantiomeric pair. It is known as the enantiomers. I'm coming to the diastereomers. The optical isomer that having a non-superimposable as well non-mirror image relationship to each other is called as a diastereomer. I will take an example of lactic tartaric acid. Here, three possibilities: D-tartaric acid and L-tartaric acid and mesotartaric acid. Here, clearly observed, D-tartaric acid and mesotartaric acid both are non-superimposable and also non-mirror image relationship. Here, both D-tartaric acid and mesotartaric acid and diastereomeric relationship, and also mesotartaric acid and L-tartaric acid are also non-superimposable and also non-mirror image relationship. So it is called as a diastereomic relationship. It is clearly it is understanding for the another type of system that is called, that is all possible structure with mirror image relationship is compared side by side. Here plus or D-tartaric acid or minus or L-tartaric acid both are mirror image relationship but non-superimposable. It is called as enantiomer. And already discussed about the D-tartaric acid with the mesotartaric acid and L-tartaric acid with the metotartaric acid are the diastereomeric relationship. This concept of diastereomeric and enantiomeric as well as the geometrical and the chain and position conformation, all isomeric concept is a very useful for the medicinal as well as biological and pharmaceutical industry. Thank you.